All right,
Okay.
we're ready for our second talk.
Okay. Thank you. I hope you can hear me. I'm presenting the work with which we made the second place in the disparity challenge, but the work is actually about occlusions and motion and depth boundary estimation together with optical flow and disparity. And we also present the final network for scene flow. The winning of the challenge actually mostly is attributed to Tonmai Saikia, but he cannot be here today also because of visa issues. So something appears to be wrong with US visas. As a preface, I wanted to say really thank you very much, Andreas and the staff, for organizing this challenge. And I think it's a great opportunity to compare algorithms actually. So at this point, I just wanted to say thank you. And maybe it's a good opportunity to, to give them an applause. Okay, so one thing that is apparent in the challenge is really that in most disciplines now, actually except the multi-view stereo, all the disciplines are led by CNNs. So you have a CNN, you input the images, and you estimate them end to end. So this is just interesting to observe. So we ask a question, which is, now we have the CNNs, which can estimate the flow or disparity, but actually other important quantities are occlusions and motion boundaries. And for classical methods, these are very hard to estimate because they violate actually the underlying assumptions. Usually you treat them as outliers. So for example, occlusions, they violate the data term, and motion boundaries, they violate the smoothness term. So they propose a hard problem. And the other part is that they're hard to estimate. So, but overall, they're important for applications. So we asked the questions for CNNs, can we estimate occlusions and motion boundaries jointly, and how does it affect the results for CNNs? Okay, in the first step I will present the general network architecture that we use. I think much of it is a repetition of the talk before from Yi. Most things are actually very similar. So we based the work on FlowNet 2. We removed the small displacement network because it turns out you can actually train the big network to also contain this task. And then we do some small technical tricks. So this is really just a technical thing, but it has some quite big effect. So in the decoder of FlowNet C, for example, you have this deep supervision. That means that at every decoder stage, you make a prediction and you have a loss of this prediction against the ground truth. And then you also use this prediction and you reinsert it into the network such that the decoder can then step by step refine this prediction. And now what we did is we just scaled this prediction here by a factor of, we divided it by 20, and this means that internally it has to be larger by a factor of 20 such that it matches the ground truth then. So what this does is it weights these predictions or the optical flow estimations relatively to the features that are traveling in the network. And because you have weight decay, this has some effect. And you can see that this is the prediction with the old FlowNet C. This is the prediction when we scale actually these values internally. And you can see that here for the small displacement case, you really get rid of this noise. So this is just a small technical detail, but you can see it has a very nice effect and it doesn't really change the EPE. Then, this was also the same in the previous talk. We moved the correlation layer up one level, so we make the features actually deeper. So before they were after conv 2, and we moved them up after conv 3, and you can see that this really dramatically decreases the error. So having a larger receptive field here, we can only confirm what the previous speaker said, is really good. And then this prediction scaling here, you can see it doesn't change the error much. So it just has a nice effect of making the predictions very smooth. Then we also use the residual connections supposed by Pang et al. We find that networks with these residual connections, they converge much faster, but actually the result is pretty similar to not using residual connections. So it just makes the convergence much faster. So if you train this long enough, you also usually get a similar result. So finally, there are just small modifications we make to the network. So we now apply this FlowNet2 architectures to the disparity setting and to the optical flow setting, and we have these residual connections here in place. And this can also be considered an iterative refinement. Okay, so that just is this network architecture that we use for everything. And now the interesting question is, how do we integrate occlusion and motion boundary estimation into this architecture? So let me just briefly say something about previous work. It turns out that about both modalities there's not really much previous work existing, which is quite surprising because, as I mentioned before, for applications these are important. So for occlusions and flow estimations, there's the sparse to dense flow from Liardiano et al. And they train a classifier to detect occlusions, and then they use this in their cost function. Then there's mirror flow from Hoare et al., which is a more recent method, and they use forward-backward consistency to check for occlusions and use this in an optimization framework. So you know there are many optical flow methods on Sintel, but very few actually provide these occlusions. And for motion boundaries, it's very similar. So there's only one method which provides reasonable motion boundaries from Weinzapfel et al. And they also train a random classifier on an optical flow input. So the simplest thing you can do to integrate occlusions into this architecture is you can just add them as a loss here, and we call this simple prediction. So we just add a softmax loss here, which classifies each pixel as occluded or non-occluded. And then we use this prediction and insert it also into the refinement stage, such that the refinement stage can also make use of this occlusion information. The second variant, which is more akin to traditional methods, is we actually integrate forward and backward flow just into one network. So we compute this correlation into both directions, but apart from that, we don't change this network architecture, but predict forward and backward directions. So the idea here is that in classical methods, or the underlying thing is that if you have an occlusion, then the forward and backward flows are not consistent if the occlusion is filled correctly, even from the surroundings. So with this forward-backward checking, you can always find occlusions if the flow is correct. And that's why the classical methods do it with forward-backward consistency checks, and we bring this to a network architecture by integrating it like this. And the third variant is we just use this stack of networks from before, and we apply it once in the forward direction and once in the backward direction. So this is just this network applied in one direction and in the other, but intermediate we exchange the flows. So this actually gets the backward flow inserted here, and this actually gets the forward flow inserted here. So this has more power because it has more, in this one network has to do actually the task of two flows, and here you have them separately. Okay, so now these are the possibilities you have to extend this architecture. The observations we make for this first architecture is actually that the flow performance stays pretty much the same that we have here. So the flow doesn't change much. And we get very, very good occlusion estimates along with this flow, which basically come for free. So we didn't change the capacity of the network, but now we get these occlusion estimates. So this is now interesting. So what does it tell us? It tells us that this occlusion estimation joined with optical flow doesn't actually change the quality of the flow. So joint estimation of occlusions and flow doesn't have any effect. And this indicates that networks implicitly also do, when you just train an end-to-end for flow, they implicitly do some reasoning about occlusions, because when you then add it explicitly, nothing is changing. And the second observation is that when you insert it into the second network, also the second network cannot benefit from it for the refinement. Yeah, so on one hand this is disappointing, on the other hand the occlusions you get are really good, which I will show in the end. Then we have this forward-backward architecture, and we observe here that with the first network we can even observe a similar performance, but then when we add the second network, actually the performance drops rapidly. And the reason for this is that here you get a similar EPE, but the flow has different qualities. So when something fails, it fails much more rigorously than when you have this other network architecture. And then refinement is not it's not possible so well. So, and the third option actually performs pretty much the same as this. So, concluding from this, you can say that the networks, they don't benefit much from this forward-backward setup, and just using this simple prediction architecture actually performs quite well. So another way you can find occlusions is just by appearance, so you can search in the second image if the patch is appearing or not, and it seems that this does a quite good job. And also you can train a network just to predict occlusions without flow. This also works. We also show that in the paper. So in conclusion, we use this very simple architecture, or this very simple extension with the occlusions, and use this now for disparity and for flow. And here are the results. So I will show them for flow because they are actually, flow is the more difficult case. And you can see that for occlusions, we actually improve over the existing work by quite a large margin. So the best F measure was 0.47 on CintoClean, and now we are at 0.71. And for final, it was at 0.4, and now it's at 0.66. And this is just by adding this occlusion loss to the network. And for motion boundaries, you can see it's pretty much the same. So we just add this motion boundary output. The motion boundary output we actually only added in the final network because motion boundaries are some details you only want in later refinement stages. But you see also the improvement here is very large. Okay, so the conclusions are the simple approach works best. And contrary to classical methods, the CNNs do not benefit from joint estimation. They do not benefit from forward-backward estimation, but they provide really, really good estimations of these occlusions and motion boundaries. Okay, so now I will show a video demonstrating this. Okay, so here we apply this architecture now to the disparity setting. And you can see this is the old disparity, the old DispNet-C. This is the CSS stack we have. And you see that there are many more details and they're very close to the ground truth. Also these small values in the background. Here you see a large displacement case, and you see that by shifting this correlation up, we get much better results for this large displacement case. Okay, now we add the occlusions and the motion boundaries, and we apply it to flow and disparities. So you can see here are the estimations. This is the ground truth, and you can see really that we are quite close to this ground truth, and we get quite nice, sharp details. So the catch is that I said before that this estimation of occlusions and motion boundaries works really well with CNNs, and basically without increasing the network architecture, you can just obtain them for free. Here we show a few examples on the Davis challenge. just as an indication that this can be beneficial for motion segmentation, we also do some motion segmentation experiments in the paper. And here you can also see that these boundaries, they capture the moving objects quite well. Okay. Just as a last thing, I would want to mention one other paper that we submitted to ECCV, which is about uncertainty estimation. So I think in future this can also be very important for disparity and flow estimation in terms of robustness also, that the underlying model can also supply an information about how certain it is actually about this prediction. So I think future research can benefit from this quite a lot. Okay, thank you very much for listening, and in future we will have our archive paper, and we are looking forward to it.
All right, we have time for questions. Please walk up to the microphone if you have a question. Come on, what kind of an audience are you? There must be some questions.
Okay, so thank you for the talk, and I have a little question is because most of the work is kind of depending on the strong supervised data because you have especially synthesized data. So, but most of the suppose we have kind of a lot of stereo images captured from autonomous driving. So, but we really don't have the dense kind of correspondence ground truth from like laser or something else. So is there any kind of good way that you can extend the similar framework to kind of unsupervised learning without the ground truth? Thank you.
Yeah, that's actually a very good question, but I don't have a real answer for it. So for the flow, we actually have another work, or there's also already one, which is called guided optical flow estimation. So you use another method. You estimate flow as with a traditional method, and then you train a CNN against this. And it turns out this works like really, really well, and sometimes even better than having the true ground truth. But in this case, you want ground truth for occlusions and motion boundaries, and that will probably be hard to obtain. So the only thing I could imagine is that you kind of mix estimation of flow and estimation on synthetic data with a ground truth for motion boundaries and occlusions. And maybe then you can transfer this occlusion and motion boundary estimation from the synthetic data to the real data.
Thank you.
Hello, it's beautiful work. Since this is the robust vision challenge, how did your algorithm perform across various data sets? Were there some where it did better or some where it did worse?
I think we're not doing so well on the Middlebury data set yet, but I'm sorry, I'm not sure about that. So actually my colleague is the expert for that.
Okay. And I had another sort of, again, detailed question, which was, when you do training and tests, for example, on Syntel, is there a big gap on just the raw scores when you test yourself on the training data versus on the test data? Because sometimes these learned networks tend to overfit the training data.
So you mean in a fine-tuned case or in a non-fine-tuned case?
No, in your final network, if you can get a numerical score on training by just basically doing a self-evaluation. Does it drop significantly on test or not? I'll take the question offline.
Yeah, I'm not sure.
Thank you.
So I also have a question. So it's very impressive that, as you show, the network can somehow build its own model of occlusions. If you think about optical flow and possibly multi-view or multi-baseline stereo, the real power of occlusion analysis would come from using more than 2 frames. Have you thought about at all, because then you can track background regions disappearing and reappearing, have you at all thought about how this could be integrated with a network that takes more than 2 frames as input?
Yeah, so this is actually our current work. So that's exactly what we want to do. In the occlusion regions, it's you can only do interpolation if you have 2 frames because there is no correspondence. But when you consider trajectories along a longer time, then of course you can extrapolate these trajectories into the future and fill these occlusion regions. Yeah, and apart from that, multi-frame approaches are very rare still. So we think that this is also a future direction of research.
Great.
One short question. You mentioned this magic scaling factor of 10 or 20, right?
That's a secret. I shouldn't have told it to you.
How did you come up with this number, or is there any motivation?
No, it's purely empirical.
All right, one more question.
Hi, can I ask some more details about occlusion? So when you say that, so you train like occlusion and also the flow together, there's no basic performance difference, like the numbers stay the same. So do you actually like quantify the errors in like this, well, it's actually inside occlusion area and also the areas without any occlusion? I think like it's kind of like in Sintel or a lot of this kind of data set which has a lot of occlusion, the final like mixed APE is a little bit actually it's kind of like just kind of misleading, because for all this like kind of occluded area you actually cannot really do very well with 2 frames. So I guess in your case you like, because you have a very sense of occlusion, you should make a difference in these 2 areas. So I'm just curious about like the number. Do you have some like statistics for that?
No, that's a good point. So we haven't done any extensive analysis, I'm sorry. But what we have done is we have looked at the images qualitatively. And what you can see is that if you do estimate occlusions and motion boundaries jointly, then you also get much sharper flow boundaries. So that's an indication that the flow, well, is also using these other quantities. It's just the overall error doesn't change. But you're right, also maybe on Sintel, other factors dominate the final result, and maybe one should do a much more extensive analysis on this also on other data sets.
Okay, thank you.
All right, let's thank the speaker one more time. I'll take a coffee break till 10.